problem 2E, it says, determine the total force on a dam that is rectangular. It is 100 meters wide by 40 meters high. And if the water level is at 35 meters, recall that the water has a density of 1,000 kilograms per meters cubed. So let's draw a picture and we can see where I got a little off on the test. So imagine this is our face of our dam. It is 100 meters wide, and it's definitely not to scale, but it will work. And it's 40 meters high, but the water level is only at 35 meters high. So later in this process, we're gonna need the depth, and what I did incorrectly on the test was I used the height of the entire face of it in that calculation of depth instead of starting from the surface level, which is at 35 meters high. So some formulas we want to keep in mind is that force equals pressure times area, and then pressure is given by our density, our gravitational constant, and then h, which is our depth. So to find we want to do a test strip, and we're going to find the force on this test strip. So what do we need for it? We need the area of it first. So to do the area of it, we're going to imagine these are our axes. We got y and we got x. So this distance right here, that is just a change in y. So let's write that down. Down here we got change in y, and then multiplied by the width of it, which is 100 meters. We can do that. And then now we need to do the pressure element of this. So the problem tells us that the density is 1,000 kilograms per meters cubed. And then the gravitational constant is 9.8 meters per second squared. And then we need the depth. So, and one of the great reasons that we use a strip like this is because it has a consistent depth throughout, so that the pressure will be consistent on it. And yeah, so the depth, you can do it a couple different ways, but the way that I like to think about it is this distance right here, that's y. And the entire distance is 35. So if we want to find the depth, the distance below this surface right here, we can just take 35 minus y. 35 minus y. And so now what we're attempting to do is find the force on the entire face of it. So while this gives us the force on this strip, we want to add up a bunch of little strips, and what we use for that is an integral. So the integral will be set up. We want it from 0 to 35, the entirety of the face. Okay, and we know that we can take constants out front. Oh, and we're going to leave the units behind until the end of the problem, but we know where they're at right now. So we can take our constants out front, and just to make sure, we're going to use the calculator. 1, 2, 3 times 100. Cool. So we bring 980,000 out front, and we're left with 35 minus y dy, and we can solve that integral, and it'll be integral of 35 is 35y. And then this negative y would be negative y squared over 2. And we will be plugging in 35 and 0. So 35 times 35 minus 35 squared over 2. And then we would be minusing after we plug this 0 in, but the 0 is going to make both of these 0, so we can just think of that as 0. And let's not forget, we got this guy right here. Okay, so I'm going to use my calculator. 35 times 35 minus 35 squared divided by 2 is 612.5. And then we're going to multiply that by 980,000. 980,000. Cool. And then the answer for this part is 650. Make sure we wrote that down correctly. 4 zeros. Cool. And now let's go back and let's figure out what our units were. So up here, this is kilograms per meters cubed. This element is meters per second squared. This depth right here, that would be in meters. This width is in meters. And so is this thickness, this dy. So we can cross these out. Those cancel those. And then what we're left with is kilogram meters per second squared, which is a Newton. So that's our final notation. Yeah, that's it.